Hi everyone, this is our presentation video for the Mechatronic System Design Group Assignment. Our team consists of Ang Yi-kun, Jonathan Chawali, and myself, Lo Bao. For this project, we have designed Spidey, a spider-style rescue robot built to handle challenging environments. So without further ado, let's begin with the problem statement. Imagine an earthquake zone, collapsed building, shifting rubbers, gaps too narrow or unstable for human rescuers. Conventional field or track robots broke down on debris and can't switch through tight space. The result, critical delays in finding survivors and accessing hazards. Our problem statement is simple. How do we reach and inspect places that are too dangerous or outright impossible for people and traditional robots? We need a platform that is compact, highly maneuverable, and able to adapt its body to unpredictable terrains. So, to address this challenge, we have developed a spider-style rescue robot called Spidey. With 4 articulated legs and 12 degrees of freedom, Spidey can step over, crawl under, and balance on rubbers where wheels fail. Independent legs control lets the robot can first step over obstacle up to 20 mm high. The second maintains balance on slope or loose surface by adjusting body pitch and roll in real time. And then the third one is go through gaps only 150 mm tall. All of this is powered by a single 18,650 battery and controlled by an ESP32 with onboard Wi-Fi. So our team can drive and monitor the robot from a safe distance. Okay, now I'm going to introduce the design specifications for Spidey. So the first one is geometry and weight. Footprint no larger than 300 x 300 mm. Overall height is less than 150 millimeters, and total mass is less than 700 grams. That's keep the center of gravity low and the servo within their top limit. And then the second one is about the kinematics. 4 legs times 3 degrees of freedom give us 12 active joint. The hip yaw range is plus minus 55 degree. Hip pitch is negative 30 degree to positive 75 degree. Knee is 0 to 90 degree. This range delivers an 80 mm strike at up to 3 steps per second. So the third one is performance target. Cruise speed of 0.2 meter per second, endurance of 20 minutes on one charge, and body roll or pitch held within plus minus 5 degree on uneven ground. So we are now looking at the control and sensing. An ESP32 runs dual PID loops for balance and velocity, while a BNO 055 IMU supplies drift-free operation data. So Wi-Fi gives us a web GUI for live tuning. And then about the power and safety, a buck converter fixed 5 volts at 6 amperes 12 SG servos protected by fields and low voltage cut-off. All joints are guarded and an in-stock sharp PWM to every servo in under 10 milliseconds. So the last one is about the cost and manufacturability. Entire bill of materials sits under 250 ringgit. Every single structural part is 3D printed in PLA. Full assembly takes less than 2 hours with a single hex key. So meeting this spec means Spidey can do its jobs, delivering eyes, ears, and sensors into place that humans can't reach quickly and safely. So let's conclude the big pictures about the problems, solutions, and the spec that hold it together. Next, Jonathan will show you how we model the robot's dynamics and tune the PID controller that makes Spidey work. That's all from me. Thank you.
Thank you, Bao. Now we talk about the system modeling. So for the moving system modeling, we have a moving system is the forward, backward, and also the turning of the robot. So we input the velocity y and also the heading of the robot, and then it will go through a PID system. Then it will control the speed of the leg, which will execute the leg movement sequence, which controls the sequence of the leg movements, and also it will output the XYZ to servo angle. So and then it also has IMU feedback to make it a closed loop system. So for the leg movement sequence detail block diagram, we convert the speed of the leg to sample it and then convert it to discrete form. So this discrete form has a goes through a gain and also delay block. So this delay block controls the sequence of the legs. So each of these signals correspond to one of those legs. Now let's talk about the balancing system modeling. So the balancing system modeling is how the robot is able to maintain the pitch and the roll of the robot. So with the pitch and the roll of the robot, with a desired pitch and roll of the robot, it goes through a PID system, and then it outputs a Z reference. So Z reference is how much of this leg to go up and down, so that it's able to maintain the roll and pitch. So we have a speed limiter here to make sure that we don't accidentally so that we're able to precisely control the speed of the position and the speed of the leg, and then obviously it has to go through a XYZ to servo angle converter, and it goes to the output. So and then it also has an IMU feedback. So this is how we map the XYZ to servo angles. We have the first servo, second servo, and third servo here. So each of them has the angle that is calculated using the law of cosine and angles. So this is the simulation on the leg movement for the X, Y, and Z movement. So for the sensor, we're using inertial measurement unit in 0055. So this talks about the physical characteristic of the sensor on how it's able to produce this capacitance when there is a displacement, and then using the change in capacitance and also the sensitivity of the IMU, you're able to get the angular velocity of the IMU of the robot. So by applying a bit of noise and bias, and then finally we integrate it with respect to time to get the position of the robot. So we choose this IMU because it has high accuracy and it uses accuracy communication, so we can get the data directly, and there's also no filtering needed because everything's already processed on board. So the actuator we're using is Servomotor SG90. So this is the block diagram. So this is a position control DC motor. So yeah, it takes in angle, goes through a position PID, then outputs the velocity, then goes through, then converts to torque, and then finally is able to achieve the desired position we want. So the reason why we choose Servomotor is because first of all, it's lightweight and it's also able to achieve the desired specification we want, as each of these servos is able to lift 2.5 kg per cm, output 2.5 kg per cm torque. So with 4 legs, we calculated that the maximum body weight should be around 0.752, which is way higher than our final robot. So it's also compact size, so it doesn't require much 3D printing for the sockets and the housing. It's also low power consumption, as it only draws around 150 to 250 milliamps. So we don't need a very big power supply for our CHUA servo system.
So thank you, Jonathan. So next, let's see what is the other electronic hardware that we use inside the Spidey robot. The first one is ESP32, which is the main controller. You have dual core processing power and able to handle the calculation in real time. Next, it has more GPIO pins, which is around 25 usable GPIO, as normal Arduino Uno only have 40 digital pins, which is way not enough for the project. And lastly, it has a built-in Wi-Fi and Bluetooth, allow us to do a remote control without needing other extra module. Next is the 5-volt regulator, which is the MP1584EN. It has a high efficiency compared to normal linear regulator that only has 40 to 50% efficiency. And the most important thing is it has really small size, which is 22mm times 17mm times 4mm, that allows us to fit into the body chassis where space is really limited. And lastly is the battery that we use. It's the AMT1N650 battery that is 3005 mAh. It offers a high capacity and energy density that allows us to run the spider robot for 30 minutes non-stop. Next is the electrical block diagram for all the electrical components that we use. Due to each 5-volt regulator only support 3A, which is equivalent to 6 servo, so we put 2 5-volt regulator, and we took one of the 5-volt regulator to support the power supply for the ESP32, and another one is to the IMU. And as you can see here, we managed to fit all the pins, which is 12 servo pins, 1 button pins, 2 IMU pins, and 3 LED pins with just into a ESP32. And this can be achievable by the normal Arduino. Next is the both electrical and mechanical system that we do. This is the drafting for the wiring, as we need to make sure that the board size is within specification so they can fit into body box of 70mm times 90mm times 20mm. So we organize the item on the donut board and we draw out the wiring diagram as shown. Not only that, we also draw the CAD drawing in SolidWorks, as you can see here. And this is the final output. And this is the actual donut board that we sorted out, and we managed to fit into the body chassis as drawn inside the SolidWorks. Then let's see the control system algorithm that we use inside Spidey robot. First is the PID control for the roll stabilization. This is to keep the robot roll, which is tilting left or right, at the desired level. And also we made a PID control for the pitch stabilization, which is to maintain the front to back posture. And by combining this and input into the Z, which is the height of each leg, we managed to do the stabilization for the robot. And also we do a PID for velocity control of the motion, and it will always compare the curve velocity to the target velocity and uses a PID control to calculate how much correction is needed to reach the target speed. And the calculated speed is then passed into the actual speed of how fast the servo moves, so that spider can walk exactly at the speed that we wanted. let's begin the demonstration video with the moving motion of the spider robot. So at the start, one leg will be shifted towards the front and the other three legs will push to the back. And this will eventually make the body move towards the direction we wanted. And let's see how they perform on a soft surface.
Okay, stop. Turn.
As you can see here, it successfully performed the task of walking forward and also the turning on the soft surface. And not only that, it's able to perform the same task on the hard surface too. Besides from normal walking and turning, it's also able to change its height when it's walking and also turning. Besides from changing height, let's see how they walk on uneven surface. And lastly, let's see how they do the body balancing on an uneven surface. As you can see here, it doesn't matter how I tilt the panel, it still managed to maintain its body at 0-degree level. And
Hi, so this is the demonstration in the real scenario. So now I am going to connect the phones to control this remote. So this one we use the Bluetooth based GUI to connect the Spidey. Okay, connected to the Spidey. Okay. Now we will let the robot to do the task one, pass through the obstacle. So now I will let the Spidey pass through the obstacle. So to pass through the obstacle, I increase the height of the Spidey. So you can see the Spidey is successfully passed through the obstacles.
Go.
Okay, so now I will let the Spidey pass through this uneven surface. You can observe that the Spidey can maintain its balance at the uneven surface. Okay, now I will let the Spidey go through the tight space. You can see the Spidey is now go through the tight space.